Welcome to day 12 of a question a day. So we have this function which is a quadratic divided by a linear, and they've stated, x can't be -2 or it would make that denominator 0. And the first thing they've asked us to do is express that function in the form ax plus b over x plus 2, stating the values of a and b. Right, well, it looks to me like the answer to a polynomial division. So I think that's what I'll do. I'll start off with A. I'll actually work out how many times does x plus 2 go into x squared plus 6x plus 12. So I'm doing that polynomial division. So that would be x times x is x squared, x times 2 is 2x, subtract 4x, bring down, there we go. Now to get 4x, I've got to times the x by 4, so that's 4x plus 8, and I end up with 4 down here. So what that's saying, sorry, I'll just remove this out of the way, and just give me a little bit more room. Okay, so what that's saying is that x squared plus 6x plus 12, when you divide it by x plus 2, you get x plus 4, and then you get 4 remaining out of x plus 2, which you haven't divided fully and got a response to there. So that's what that is saying there. Now the question actually said, don't just express it in that format, but also you need to write what are the values of a and b. So like this is like 1 times x plus 4 over x plus 2. So a is equal to 1 and b is equal to 4. To make sure that I've specifically answered their question. B, write down an equation for each of the two asymptotes. Okay, so our equation was that we had x squared plus 6x plus 12, y is equal to this on x plus 2, which was equal to, and just let me go up, which is equal to x plus 4 on x plus 2. All right, so we want the asymptotes. Well, it's easy to see from the original equation that x cannot be minus 2, which means we're going to get a vertical asymptote at x equals minus 2. Vertical asymptote at x equals minus 2. But the question actually said to us to write down the equation for each of the two asymptotes. Well, I don't see another vertical asymptote, and there's no square roots to limit things. So the other thing you often do is look at what happens to the function as it gets very large or very small, and that's easy to do when it's written in the format, the second format. That is, when it's written like this. So that's what I'm going to do. X plus 4, right? As x approaches infinity, x plus 4 on x plus 2, right? As that happens, that approaches, well, x plus 4 gets just massive, doesn't it, right? Infinity plus 4. But 4 on x plus 2 approaches 0, doesn't it? Right? So it just approaches x plus 4, all right? Because 4 on x plus 2 approaches 0, right? If you're going to divide by massive number, that part there just approaches 0, all right? Which means that it's not approaching a particular number, but it's approaching the line y equals x plus 4. So we've got like an oblique asymptote is the y equals x plus 4. So there's our two asymptotes. They're both lines. Normally we have just a vertical and a horizontal one, or a couple of verticals and a horizontal, but we've got an oblique one here, which was easy to find. Okay, the next question then, after getting the asymptotes, was show that it's got two stationary points and determine the coordinates and nature of the stationary points. So I'm going to use the way we've been told to write it, x plus 4 on x plus 2. And I'm going to differentiate it using that. So the first derivative is, well, the derivative of x plus 4 is just 1. And this here is actually 4x plus 2 to the negative 1. So it'll be 1 minus 4x plus 2 to the negative 2, wouldn't it? I.e., that's 1 minus 4 over x plus 2 squared. And then the second derivative is, well, the derivative of 1 is 0. Now, once again, it would have been easier to write that as minus 4x plus 2 to the minus 2. Then we can see that it'll be 8x plus 2 to the minus 3, which is 8 on x plus 2 or cubed. So let's just write them down neatly so we can see what's going on this next page. Y is x plus 4 on x plus 2. The first derivative is 1 minus 4 on x plus 2 squared. And the second derivative is 8 on x plus 2 cubed. Okay, so we're going to use those now. We've been asked to do the following. I'll just go back to the question all the time, just check what I'm asked to do for part C. Show that there's two stationary points, then determine the coordinates and the nature of them. So, for stationary points, dy dx equals 0, doesn't it? The first derivative is 0. So 1 minus 4 on x plus 2 squared equals 0. So 4 on x plus 2 squared equals 1. So x plus 2 squared equals 4. So x plus 2 squared minus 4 equals 0. X plus 2 squared minus 2 squared equals 0. So x plus 2 and x plus 2 minus 2 equals 0. So x plus 4 and x equals 0. So x equals 0 or minus 4. X equals 0 or minus 4 gives me stationary points. I might as well find what those points are. So when x equals 0, y equals, and I put it in up the top. I've got my equation for y up here. Y is 0 plus 4 on 0 plus 2. So 4 plus 2, y equals 6. And when x equals, what was the other point? Minus 4, y equals minus 4 plus 4 on minus 4 plus 2. So 0 and 4 on minus 2 is minus 2. Okay, so we've got our coordinates of our stationary points, 0, 6 and minus 4, negative 2 are the stationary points. I'll just put that there so I can find it if I need it. Now, I've got to determine their nature, so I'm going to try the second derivative test. When x equals 0, the second derivative is equal to 8 on 0 plus 2 cubed. equals 8 on 8, which is 1, which is bigger than 0. So that's meaning it's like concave like that, right? So it's concave up. Therefore, the 0.06 is a minimum turning point. Okay, and then what about when it's -4? When x equals -4, what's happening with that second derivative? Well, it's 8 on -4 plus 2 squared, which is 8, cubed, which is 8 on a -2 cubed, which is 8 on -8, which is -1, which is less than 0. So it's concave that way, which gives us a maximum. So therefore, our point -4, what was it? -4, -2 is a maximum turning point. All right, so that's going to help us. So I'll just check I've answered part C fully. It says show that it's got two stationary points. Done that. Determine their coordinates. Done. Found the nature of them. Yes, minimum and maximum. Sketch the graph. Okay. So I just need to okay, need to go down to get myself some room down here to sketch the graph. So let's come back up. All right, to sketch this graph, so we're going to need to, we're going to have to go up to 4 and have to go over to -2. So -2 is going to be a vertical asymptote that we found. And we found that the line y equals x plus 4, so that'll go through at -4 as well, right? This line here is an oblique asymptote. We found that the 0.06 right there, that's the 0.06, it's a minimum turning point. So we obviously come down and we head like that. And we found that the point -4 and -2, so the point there, I'll call it -4, -2, is a maximum turning point. So it goes like that. So there's a bit of a sketch of it. And then we need to find out what's the last question wanting us to do. So it says, state the range of values of k such that fx equals k has no solution. All right, so fx equals k, that means it's a constant, all right? Now, all lines fx equals k are just horizontal lines. For example, I'll draw, that's f of x equals 2 as such, if y equals f of x, right? That's y equals 2. And that's a horizontal line like all of the fx equals k's, but that doesn't cut through the graph at all because the graph has a maximum turning point down here but a minimum turning point here. So anywhere between that y value of -2 and that y value of 6, you can draw horizontal lines all you like and you're not going to cut through the curve anywhere in here, right? So if you want to make it so there's no solution, then you want to have k in between -2 and 6, because k is a horizontal line and it won't touch the curve between y equals -2 and y equals 6. Just check that I've answered that. State the range for which it has no solution. Yeah. between -2 and -6. All right,